Honors Algebra 2, Chapter 2, Section 7. We're going to graph absolute value equations. Yesterday we did piecewise functions. We're going to use those a little bit to introduce absolute value graph. Now let's first graph these two equations. So y equals x. Students struggle with this equation at the beginning. It should be one of the easiest ones. There's a few ways to graph it. You can make an xy table. If x is 1, y has to be 1. If x is negative 2, y has to be negative 2 because they are equivalent. The other way to look at that is in slope-intercept form. This is 1x plus 0. So you can plot it with the 0 and then increasing here. So it should be one of the easiest equations to graph, but students always get stuck on that. And so here's the equation. Here's the line. And we can also graph the second one, y equals negative x. Same thing, it's just that y is the same as the opposite of x, or y is equal to negative 1x plus 0 if you want it in slope-intercept form. And so we can plot these points. We're going to apply at 0, and then down 1, up 1, or up 1, left 1, however you want to say that. And then we can connect that. So you get a nice little x there. Now if we graph those same two equations, but as a piecewise function, so here's where that piecewise is from yesterday. So this is y equals x and y equals negative x, but we have these domains. We only want to graph y equals x if x is greater than or equal to 0. So x is greater than or equal to 0 from this point right. And so when we graph y equals x from this point right, we're only graphing this upward trend of that equation, of that line. And if we graph the other portion, y equals negative x, is when x is less than or equal to 0. So y equals negative x is the upward trend going to the left. So we get this shape. Together, these actually make the absolute value of x. This is the graph of y equals absolute value of x. Another way to describe that, if I have the absolute value of x equals 3, we stated earlier on last chapter that x equals plus or minus 3, that x will be the positive negative value of that. And that's the definition, that if y equals the absolute value of x, then that's equivalent to plus or minus x by definition. And so that's what we just graphed. We graphed the plus and minus x. All absolute values have this shape, the V shape. If we graph another one, let me just make up a basic one. We said y equals absolute value of x plus 2. Now there's some math that's being involved in here with the x. So if we actually make a table to help us out with this, and I plug in some values. So if I plug in like a negative 2, 0, and 2, let's try applying those. So if I plug in negative 2 plus 2 is 0, absolute value of 0 is 0. I plug in 0, 0 plus 2 is 2, absolute value of 2 is 2. I plug in 2, I'll get 4. Let's do some more points. Let's do some negative ones, more negative, negative 4. I put in negative 4 plus 2 is negative 2. The absolute value though of negative 2 is positive 2. So we plot these points, negative 2, 0, 0, 2, 0, 2, 2, 4, negative 4, 2. So we have this shape. You still have the V shape here, and you might need to plot more points to see, but you get this shape. The only difference between the purple-red one we graphed and then the blue one is that it's been moved left 2 spots. And that corresponds to that plus 2 there. That's actually by a horizontal shift left 2. So the parent function that we talk about, y equals absolute value of x, is this graph we originally graphed. All we're going to do is we're going to take this function and we're going to move it left, right, up, down. We'll flip it, we'll stretch it, but that's the parent function. So the form of that parent function is this, which includes all the different parts, where our a value here vertically stretches the graph. It's also known as the slope to the right of our vertex. The HK is the point. HK is the point or vertex of the V. The point of the V. H is the opposite of the number in the equation. So if I had like a x minus 3, H is actually positive 3, the opposite of what you see. So if we try graphing 4 here, if we pull out the information, we should see that the vertex, our H value, is opposite of negative 3, so it's positive 3 and then 2. The slope in this is the number being multiplied to the absolute value. For 1/2, it is the A value. So then if I graph the vertex first, 3, 2, then I use the slope to the right, up 1, right 2, up 1, right 2, up 1, right 2, and I connect those points. That's just the right-hand side of the absolute value graph, the V. If I go up 1, left 2, I'm going to get the other side of the V. So there's the other side of the V. So this is the absolute value. Notice how this graph from the original spot, which was the origin, has been moved right 3, up 2. And that corresponds to our 3, 2 in our vertex. And then it's now opening wider than the parent function because it has been vertically shrunk by half, so it doesn't increase as much. Another way to say it, if I go right 1, I'm going to go up my A value. Let's do the next one. So we have that y equals the negative 2 times the absolute value of x plus 4 plus 3. Our vertex here is going to be negative 4, 3, hk, and our slope here is negative 2. So we plot that point, negative 4, 3. And then using our slope, I can go right 1, down 2, right 1, down 2, or down 2, right 1, however you want to say that. So we get this V. We also do to the left. Left 1, down 2, or down 2, left 1. Goes both directions. That last point is a little off. So here's the V. It's opening downward, and it's from geometry. You might remember that that negative A value reflects the shape. So instead of going upwards, it's downwards. You've seen that before in geometry, and also in algebra with the parabolas that have been reflected or flipped. So quick problems here. Let's evaluate the expression negative absolute value of negative 7. For that, the absolute value of negative 7 is 7, and then you have another negative that turns it into negative again, so it should be 4, negative 7. For 2, we plug in r and plug in s into this expression. Absolute value of 2 is 2, minus the absolute value of negative 7, which is 7, so we end up back to a negative value, negative 5. 3, we should be able to write the equation of the graph. So for here, we can't really see if there's the slope on this. So we assume it's 1 to 1, but we can use the point here, 3, 1. So the point is describing our h and our k value. So in our equations over here, it can't be 2 because it's not an absolute value, and our shape is an absolute value of v. So it's got to be one of the other 3. Since we move it right 3, I know the h value should be negative 3. Now I see 2 negative 3's here. The difference though is this one is being applied to the x. Our h value always applies to the x because our h value is how far it moves left and right. So it has to be 4. The number outside the absolute value is the k value, which moves it up and down, and that would be 1 for this graph. So again, on 4, same kind of problem. We don't have an h value, or h value is 0, but we move it up 1. So we don't apply anything to x. We apply it outside, and we go up, so it's positive 1. So there's the equation of that graph. Well, a different one. The graph below represents f of x, so this line is f of x. What would the absolute value of f of x be? Now, see that we're taking the absolute value of f of x. The absolute value is going to be the distance of f of x from 0, so it must become positive. And so if we take all these y values down here, they can't be negative. They're actually reflected and become positive. And so we get that V. So it's got to be this graph. Question 6. This is your problem to do tonight. Turn it in when you walk in the door. Graph it. Make sure you're careful on your H value. Have a good night. See you tomorrow.